Okay, uh, let's begin the actual material. This is chapter 1 of Giancoli. I'm pretty sure I didn't copy his title for the chapter, but I'm emphasizing the items that I'm going to be talking about in this chapter. A very short treatment, and there are several topics that Giancoli treats that I'm not going to talk about and won't be important for us in the course. Some of this stuff is just reviewing things that you likely learned in high school or even before. So we'll start out talking about dimensions and units. Most people know what units are, but maybe not dimensions, so we'll briefly talk about that. Scientific notation, how to express quantities in scientific notation, and the SI prefixes like kilo and centa and that kind of stuff. Then how to change units of physical quantities, which it's always good to review because we'll be doing that, occasionally throughout the course, although we'll mostly be sticking with SI units. That does come up. A very brief discussion of significant digits, in other words, how many digits you specify when you specify a physical quantity. And finally, something called dimensionally balanced equations, which I'll explain when I get to it. So, starting out with dimensions and units, one of the questions I often start the course with is, what are some measurable properties of things or events in the universe? In other words, if I watch a pair of spheres collide and bounce off of each other, what are some things I might measure about them? Well, I might measure a time duration. I might measure the length of one of the balls. I might measure the volume of one of the balls. All of those kinds of things, the speed of one of the balls, all of those various kinds of things that we might measure about some event or some object are things that we call dimensions in physics. So some examples of dimensions that we'll be seeing in this course: weight and mass. Weight and mass are actually different kinds of dimensions, but they're related to each other, and we'll talk about that later on. The length of an object along a certain direction, the volume of a 3D object, rotational rate, how fast something is spinning, the energy, we'll define that later on, and temperature. Normally in Physics 110, we would cover that at the end. If you're listening to this because you're part of the online course during the pandemic, we won't actually get to that this semester just because the time we have for the course is a little bit foreshortened. So you might think this is a little bit overwhelming. We might be treating 25 different kinds of dimensions in the time we spend in this course. But the good thing is a lot of the dimensions can be expressed in terms of a smaller set of dimensions. So for example, if we're measuring the speed of an object, we can just calculate the distance it went divided by the time that it took to go that distance. And so I don't need a separate dimension for speed because I can express that in terms of the simpler dimensions of distance and time. We're going to use that to our advantage to sort of help us sort out all of these different kinds of dimensions that we have up here. And the amazing thing is that in Physics 110, all of the dimensions that we are going to have to use in this course can be expressed in terms of three what we might call fundamental dimensions. Not everyone agrees on what the fundamental dimension should be, but for us, length, time, and mass, how much heft there is to an object, those are going to be the only ones we fundamentally need, and all the other dimensions we'll be able to express in terms of those three. That's not to say that those are the only three. There are other ones, such as electric charge, or temperature is actually a fundamental different dimension. So if you go on in physics, you'll encounter other ones, but this is all we'll need for what we're doing this semester. Now, the difference between dimensions and units, if I decide on a dimension, such as length, there are always lots of different ways that I can express length using what we call different units. I could express a length in feet, I could express it in meters, I could express it in miles. There are lots of different ways. And so for each of these fundamental dimensions, length, time, and mass, there are different ways we can express them in units to make a measurement. So just for a random example, length can be measured in inches, time might be measured in days, and mass might be measured in what some time ago was the English unit for mass, which was called a slug, but it is a certain amount of mass. And another example is I might choose to measure length in feet, time in years, and mass in grams, and that's a different way to express those. We are going to very closely, just for simplicity in this semester, stick with what is called the SI unit system, the International System of Units. And the unit we're going to use for length, which most of you are somewhat familiar with, is meters. The unit for time is seconds, and the unit for mass is kilogram. Notice that it's not a gram, it's kilogram. And so in most of the course, we're going to be using those three units for the three fundamental dimensions. And for other dimensions, things like velocity, acceleration, energy, we'll express them in terms of those fundamental SI units. There are ways to convert between different units. In other words, if I have a unit, a dimension that's expressed, or a measurement that is expressed in a certain unit, I can always convert to other units for, equivalent units for the same dimension. For example, things like 1 inch is equal to 2.54 centimeters. That's what we call a conversion factor, or a conversion relation between these two units. And there are lots of them listed in the back cover of maybe the front cover of your book, or you can just Google them to find out what conversions between units are. If you're doing homework and something's expressed in inches and you want it in meters, you can Google what the conversion factor is, and we'll practice using those in just a bit. Okay, so that was on dimensions and units. Now let's talk about scientific notation and the SI prefixes like kilo and the like. So why do we want to use scientific notation? What's the motivation? Well, there are physical quantities. For example, here's a list of distances that physicists might be interested in, and they span a huge range of different physical distances. For example, at the time I grabbed this from the web, it's probably no longer current, but the distance to the farthest galaxy was estimated to be 10 to the 26 meters. If I wrote that out in the standard way of writing it, that would be a 1 with 26 zeros after it, which is sort of inconvenient. If I want to write that down, I'd hate to be writing the 26 zeros every time I was writing it down to give the information to somebody else. That's a very large distance. It goes through lots of different distances down to very small distances. This is by no means the smallest one physicists use, but for example, the approximate size of a proton is about 10 to the minus 15 meters. That would be a 0 point and then 14 zeros after the decimal point and then a 1. Also very inconvenient. So we don't want to have to write them that way. We'd rather write them using scientific notation. So one of the advantages of scientific notation is that you can specify very large or very small quantities with ease, whereas in the standard decimal notation, it's not so easy. Let's just take an example of why we might be interested. For example, if we look at the approximate distance from LA to New York City, if we express it in meters, that would be 3,961,000 meters. And if we write it the standard way, that's pretty cumbersome. So we can save ourselves a little bit of effort by writing it in scientific notation. And in scientific notation, what you do is move the decimal place, which is, it's sort of implied after the last number in the standard notation. We move it to the left. Maybe I should use my pointer here. I got to get used to using that. 1, 2, 3, 4, 5, 6 places so that it comes after the first digit that's specified. So instead of 3,961,000, we put the decimal point right there. And to do that, I had to move it to the left by 6 places. And that means that I would have to, since I've made it, a factor of 10 times smaller 6 times in a row, I've essentially divided it by 1,000,000. I need to multiply it by 1,000,000. That's 10 to the 6th to leave the number unchanged. So I've made this number smaller, but then I've made it back bigger again by multiplying by 10 to the 6th. So however many places you move it over to the left to put the decimal point after the first digit, you multiply by 10 to that number to get it in scientific notation. So that's one way to make it less cumbersome. Another way to make it less cumbersome is using what are called the SI prefixes. So kilo, as most of you probably know, and I'll show you a table in just a second, means 10 to the 3 or 1,000. So kilometer means 1,000 meters, and I would need 3,961 thousands of meters to be equivalent to this many millions of meters. So those are two less cumbersome ways to specify something we might be interested in, a particular distance. If you look in the book, there's probably a list of SI prefixes in there, and they span things from very small, atto 10 to the minus 18th, to exa 10 to the 18th. We're really not going to use many of these, but the ones that you should know for this course, and the ones that you'll kind of see in newspapers and just common communications, are the ones I've put in a box here. So nano, like nanotechnology. Nanometer is 10 to the minus 9 meters. That's 1/1000th of a meter. So if I write little n and then m after it, that means a nanometer. Micro, 10 to the minus 6th, its symbol is the Greek lowercase mu, so that's like the Greek m, but it looks like a u with a little tail on the left-hand side. So if you see a mu and then m, that means micrometers, and that's 1/1000th of a meter, or 10 to the minus 6 meters. Milla is 10 to the minus 3, or 1/1000th. Centa is 1/100th, 10 to the minus 2, and kilo is 1,000. We're really only going to use those. Occasionally you'll see mega and giga, you know, in computer kinds of things, you'll see those appear, but for most common quantities, those are the only ones you'll have to know. And so if I use one of these prefixes, it'll probably be one of the ones in the box there. All right, that was about scientific notation and prefixes. This is just sort of a grab bag of different things that we're going to do in Chapter 1 before we go on and start learning the physics. So now about changing units. Let's just start out with what I would normally call a voting question in class, but I'm going to have you do it while you're watching this video because it's useful to think about these things in the process of learning how to do them. So a 3D printer head can move at a maximum speed of 4.00 centimeters per second. How do you express this speed in units of inches per minute? With, here I've given you the conversion factor that you need. 1 inch is 2.54 centimeters, and I'm going to assume that you know that there are 60 seconds in every minute. So what I want you to do is pause the video, take a second, take a piece of paper, see if you can work that out just from your knowledge that you know from high school or wherever you learn this kind of thing, and figure out which of these is very close to the right answer. One of them is very close, the other three are not. Here's a reminder to actually pause the video, but I'm going to go on and talk about now. Figure out the answer. I'm going to tell you a very particular way of doing it, but if you don't like this way of doing it and you're already comfortable with a different way, that's fine. I'm never going to check how you change the units on something. You just need to be able to do it reliably. So we're going to start out with the thing that we know, 4 centimeters per second, and I want to change it into an equivalent number in inches per minute. In other words, I don't want this to really change. I just want to express it a different way. And one way to take a quantity and make sure that you don't change it when you do a manipulation to it is to make sure that what you're multiplying by is actually the number 1. And one way to form the number 1 is to put something in the numerator of a fraction that's exactly the same as the thing in the denominator of the fraction. So here I know that 1 inch is absolutely no different than 2.54 centimeters. So even though this looks a little bit strange, I've multiplied by 1 in this particular ratio here, and therefore I haven't changed what we're representing at all. It's the same exact number, just different units. And now I can, the motivation for doing that, of course, was since I had centimeters up in the numerator, but I wanted inches up in the numerator, I put something that had inches in the numerator and centimeters in the denominator, and then the centimeters can cancel between the numerator and denominator in the usual way we cancel numbers. We can also cancel units that way. So we've replaced the centimeters with inches, so now I've got something that's in inches per second, and I would like to replace the seconds with minutes. So again, I'm going to do the same kind of thing. Multiply by a factor of 1. What do I put in the numerator and what do I put in the denominator? Well, I've got a seconds in the denominator, so I want seconds in the numerator, and I'd rather have minutes in the denominator. So how many seconds is equal to how many minutes? The answer, of course, is 60 seconds is equal to 1 minute. And once I do that, I can cancel the seconds. And if I look at this quantity, all I've done is multiply the thing we started with a couple factors of 1, so nothing's changed. But we've got some extra numbers in here, and the only units are left are inches divided by minutes. So if I put that all together and throw it in my calculator, 4 divided by 2.54 times 60 is approximately this number down here, and the only units that were left over were inches over minutes. So that looks like it matches very close with selection A. So the correct answer in that case is selection A. All right. Let's just step it up a little bit, and what I'm going to do is have you stop the video. Well, in fact, the video is going to end, and work on the worksheet that is posted adjacent to this video on the website. And it should start out with the problem: water flows from a faucet at a rate of 50 cubic centimeters per second. I'm interested in knowing what this rate is in cubic meters per day. So notice when I have a centimeters cubed, that's the volume inside a centimeter by a centimeter by a centimeter size cube. I'd rather have that volume specify in cubic meters, and I'd rather have the seconds expressed in days. So these are different units for the same dimension, and what I would like to do is convert this number to these different units. So what I want you to do is work that out, and when we come back in the next video, we'll explain the solution the same way we did the previous one. This one's a little bit more tricky than the voting example we just did. All right, I'm going to end the video, and I'll see you on the next video after you've worked on the problem.